Well, good evening everybody. I'd like to welcome you to this, and I don't think, is it the inaugural or the second lecture in a series run by the Institute of Environmental Design and Engineering. We're a new bit of the Faculty of the Built Environment that sort of was set up this September, and we're trying to get a series of research-based lectures running on in various topics. And tonight we're going to be talking about a project that I ran together with John Barbur and a few other researchers who I'll be talking to you about in a minute. I'm going to do a sort of a top and tail to the presentation. John Barbur sitting here will be doing all the heavy lifting, and without more ado, let's get on with it. So what I'd like to start in my introduction with is a simple discussion of what is glare, why it's important, how we control it at present. Then we'll say something about our investigation, and we'll move on then to say, well, what is wrong and perhaps things that we should change in lighting practice. There's a lot of other things that probably we need to change as well, but let's focus on lighting practice for tonight. Okay, let's start with the definition of glare that comes from the International Lighting Vocabulary, which I guess is probably the one we ought to stick with, although it's probably, as it's something that seems to be organised by the CAE, it's probably A, 16 years out of date, and B, not that helpful. A condition of vision in which there is discomfort or reduction in the ability to see details of objects, caused by an unsuitable distribution of range or luminance or by extreme contrast. And by way of an example, here we have poor contrast, and it's looking a lot worse on this slide with this projector than previously. But I don't know if you can see that, but that is an effect. Yeah, if we turn the lights down a bit, please. That's better. So now that is real glare. We're actually making things harder to see, and I think looking at that circle is not exactly pleasant, and whether it counts as discomfort or not, I'm not too sure. So why is it important? One of the key things that we would like to do on our highways and our roads at night is be safe. To be safe, we need to be able to see the things that it's important to see. So if we have glare that makes it harder to see things, then clearly that's working against it. A simple basic calculation probably would suggest that if we didn't have glare, we could have 30% less street lighting, or similarly, if glare, if you like, takes away in terms of visibility in certain situations. And secondly, it's uncomfortable, it's unpleasant, it's stressful, particularly vehicle lights and bad street lighting installations. It's mitigating against us using our streets at night. Remember, when you're lighting a road at night, you're lighting for two reasons. One is to make it possible for people to go out and use that street, and the second is to facilitate the conditions where they actually choose to go out and use that street. And so whatever we do with glare is going to mitigate one or other of those two things. Okay. So how do we control glare at present? Okay, so those of you who have been working in the area of street lighting, there's a laser pointer in here, is that it? It will recognise this beautiful document, BACN 13201 Part 2, which lists a series of lighting classes which various people in Europe can choose to adopt and use as control methods or not. And for glare, they provide us with two methods. Things called luminous intensity classes, and that's really a measure designed to control discomfort glare, and threshold increment, which is really a measure trying to control disability glare. There are a few other bits and pieces. There's some D classes, which I might mention in passing if we get there. So, the luminous intensity classes, all they do is control the relative intensity of a street light at a particular angle. So, in the UK, probably on a residential road, we'd like to go for something maybe G4 or something like that. So it says at 70 degrees, I mustn't have more than 500 candelas per 1,000 lumens. And so on a small street, that might have 5,000 lumens in the fitting. So that gives me an intensity limit of something like 2,500 candelas. And then as we get to progressively higher angles, we get progressively more restrictions. What we will do towards the end of this study, this presentation, we'll look at that again and see if that's actually useful or not. And then we have threshold increment, which is based on the concept of veiling luminance. And I'm sure John's going to talk a lot more about veiling luminance fairly soon. But we have this metric which allows us to evaluate, if you like, the veil or the luminance that appears on both object and background that we're looking at due to the presence of glare. And it's evaluated in a very standard form based on a constant of 10 and looking at the illuminance of the eye divided by the angle between the object of regard and the glare source in degrees squared. And we use that to evaluate another function called threshold increment. And threshold increment, if you like, is designed to be how much would you have to raise the lighting on a given stretch of road so that it compensates for glare. So ideally, if you lit a road to say average luminance of 1 candela per square metre, and you would get, if you had, in the absence of glare, a certain level of visual performance. To get the same level of visual performance on that road in the presence of glare, you'd have to raise it by that much percentage. And typically we limit these to something like 10 to 15% threshold increment. The question is, are these metrics right? And are they useful? Hopefully we'll come to an answer of this at the end this evening. So let's talk about our study. It was very nicely funded by the EPSRC, which is always nice when you can persuade the Environmental and Physical Science Research Council to pay you a lot of money to do some research. And it was a collaboration between 3 universities, UCL, City University, from which John Barbur comes, and there was also some work done at the Royal Holloway University. And we had a big team of people working on it. At UCL, we had 2 researchers. Navaz Davudian was the lead researcher from UCL, and she was assisted at various points during the project by Edward Burrow. Yingting was a PhD student who worked on this project at City University, as was Emily Patterson. Gary, he's a postdoc researcher, is that correct, John?
Yes.
At City University, and he helped out with certain aspects. I'm not going to discuss too much of some of the things he did. And Ali Harlow did a lot of the software programming and got all of the complex devices that we were using to work. At Royal Holloway, the whole effort at that end was led by Professor Andy Smith, and Michelle did all the spade work and a lot of analysis. The Royal Holloway work we're not going to say too much about tonight. Essentially that was functional magnetic resonance imaging of the brain, trying to work out if there are any particular regions there which became active in the presence of glare. We'll mention that in passing. And at this point, I think that's the introductions done. I think I've explained what the problem is. I think I'd now like to ask John to explain to me what his solution was.
Okay, well, thank you, Peter. Thank you for the introduction. It was a big project. We've done a lot of work. We tackled several threads, all connected with disability and discomfort glare, do you study here? How is it that you're interested in lighting? Is that what they normally do? Are you students here, or are you from outside?
I'm a PhD student here.
Right, right. And are you all interested in lighting or in
Yes.
environment and?
Because my subject is lighting, so yes.
Right, right. Well, please do ask any questions at any time. Let's make use of the fact that we have a small group, so as to make it more like a tutorial. Well, let me add a little bit more to what Peter described in terms of the various aspects of glare. You see, my part of it is to talk about disability glare and discomfort glare. Now, let me just explain this a little bit, because there are so many things which are correlated together, but they all lead towards discomfort and poor visual performance. You can't separate them very easily. But you don't need any glare sources, any bright sources to really suffer from disability glare. Look, you see this picture here? It's such a pity that the projector is not bright enough, but it's sharply in focus, it's got lots of detail. If you have increased scatter in the eye, and everybody has some level of scatter, but the level of scattered light increases significantly with age, then what you will actually see is something like this. So every point in this object is imaged on the retina. It spreads a little bit of light around, so they all overlap. The net result of it is that you are adding a veil of light over the retinal image. And what that does is to take out any fine detail in low contrast. So this picture here is equivalent to a low-pass spatial filter. Are you familiar with these things? If you take the spatial frequencies, take out of it high frequencies, they tend to have lower contrast, then you end up with these. So you get this poor vision and poor visual performance in the absence of any glare source, right? It's simply because you got increased scatter in the eye. Now, this is the extreme form of disability glare. Okay, read a newspaper with no great glare sources around, and you have great difficulty reading it. Now, discomfort glare is actually quite different in my view. It's a lot to do with the absence of a background, with the presence of very bright sources of light. As indicated here, these are LED street lamps, which I photographed in San Sebastian, in fact, in Spain. And compare that, the absence of a background, with this beautiful arrangement here, where you have a background that's illuminated, you have larger sort of sources, and more of them, and the net result of it is there's no discomfort glare, you would agree, whilst this was really quite unpleasant. Now, having sort of described the two things that I'm going to talk about, I hope you don't mind if I spend 30 seconds to just tell you where I come from. Peter mentioned City University. We go back to the Applied Optics department in 1903, that's when it started. The reason why I love this photograph is because it really shows how elegant our students were in 1903. You see, they knew how to dress, they respected the profession and the studies at City University. And this is the best I can come up with in 2014. So it's a clear disappointment. Now, but let's forget about that, let's move on. So the first study is disability glare. Remember, you don't need strong glare sources to get disability glare. And the people who worked specifically on these were Emily and Gary. And I must really pay Peter a thank you, a big thank you here, because he has seen the project, kept everybody together. There are several threads which are actually quite different, and encouraged everybody, and we are very pleased now at the end, in the sense of we made some fundamental discoveries, but also, as Peter was alluding to, the work has some impact in terms of lighting practice, and that's what we are after. So let's move on then. Now, I don't know how much you know about the eye, but because I know more about the eye, I decided to put this in. Okay, now, when you look at something, every point in the object produces a beam of light, which is captured by the entry pupil of the eye, and then it should end up at a point on the retina. So then that's how you form the picture of an object. Every point is imaged separately, right? Now, ideally, and according to geometrical optics, all these rays should end up at a point, but because of diffraction, aberrations, and scattered light, the point in the object ends up like this. So it's not a point anymore. Okay, now we understand diffraction very well. We understand aberrations. We can measure aberrations very well, which are imperfections in the optical system. Scattered light is not that we don't understand it. It's much more difficult to measure. But scattered light can cause havoc, particularly in older subjects. Now, this point image was actually taken in my eye some 15 years ago, and in green light, which doesn't spread too much within the layers of the retina here, the retinal pigment epithelium. So it's a well-defined point here, but I can assure you that 15 years later now, if I was to take the same picture again, it's quite difficult because there's a double pass technique to photograph the fundus. If I was to do that, this would be much bigger. Anyhow, as the light passes through, you see some photons, instead of following the geometric path, they will be scattered. And they end up usually around the direction of the beam, but they end up away from it. Okay, now all the photoreceptors in the eye, right, tend to point towards the center of the pupil, so it doesn't matter where they are, they point towards the center of the pupil. Remember that. Now, if there is a lot of scattered light, then what happens is every point adds more and more scattered light. You end up with a veil over the retina, and that would lower the contrast of any image that you look at. Now, just to give you an idea, that is the typical scatter function that you get away from a point source, so somewhere here, okay, for an 8-year-old. And if you compare that with a 20-year-old, which is here, you see there's much more scattered light. This is the equation which Peter gave you. He produced this equation for multiple scatter sources. We are considering what happens if you just have one scatter source, so it's slightly simpler there. Now, how does the angular distribution of forward scatter light in the eye contribute to disability and discomfort glare? Well, you see every point produces glare. As a result of it, depending on what the value of k is here, you can end up with that image, or this image, or that image in terms of what you see. Right? Do you have any questions so far? If anybody's got any questions, please do ask them. I know this has been just revision. Okay. Now, according to current knowledge, and this is important for what I have to explain later, there are 5 photosensitive pigments in the eye. 5. But it's only the cone pigments, the 3 cone pigments, which exhibit this directional sensitivity. Okay? Now, what one means by directional sensitivity, if the light enters through the center of the pupil, so then it ends up traveling along the axis of the cone, which is here, right, is more likely to be absorbed. And if it enters through the edge of the pupil, for a large pupil, is much less likely to be absorbed. Now, does this have any advantage in terms of the forward scatter in the eye, the back scatter, or for that matter, the internal scatter within the eyeball? Well, what it turns out is that it doesn't really protect us against forward scatter, because even if it's scattered at this angle, that cone photoreceptor points towards the center. But it protects us very much in terms of internal scatter within the eyeball. So, you see, in young eyes, the light passes through, it passes through the photopigments, hits the retinal pigment epithelium, which is very specular, almost like cat's eyes on the roads. and it comes out through the pupil, right? Now in older eyes, there's a lot of debris which lies on top of the retinal pigment epithelium. As a result of it, the light is scattered within the eyeball, so it forms a beautiful uniform veil there. But fortunately, very few photons, virtually all the photons, hit the photoreceptors at the wrong angle. So as a result of it, the cones will not be that affected by internal scatter within the eyeball. So this particular directional sensitivity is very important. The rods, which help us see in the dark, and the retinal and the melanopsin pigment, which is a pigment within cells that helps us with circadian rhythms and responds directly to light, they don't exhibit directional sensitivity. Okay. Now, the Stars-Crawford effect is also extremely useful because if you happen to have a large pupil, most of the spherical aberration and the aberrations in the eye, which ruin the quality of the image, they derive from the periphery of the pupil, and of course those rays are less likely to be absorbed. And that's the reason why we are protected against high levels of high-order aberrations. Now, let's go on to this aspect of the work, which is quite important. It's well known that how well you see depends on how much light you have on the retina. Really, the adaptation of the retina determines largely how well you see. How do we measure what we see? Well, we are very good at judging luminance contrast differences. So if there's an edge and a slightly difference in luminance to the background, we can actually detect that under optimum conditions with 1% difference. So we take the luminance of the target, which is here. It's a Landau C with a gap pointing to the right. The quality of the projector is beautifully illustrated here. There's no problem in seeing the gap on any screen, but here you might be pushed to see the gap. You know, can you see the gap? It's over there to the right.
It's just to make me feel good about my poor eyesight.
There is a Landau ring with a gap here. Now, the Landau ring has got a slightly higher luminance, so the difference in luminance between the ring and the background, referenced with respect to the background, expressed as a percentage, is the contrast, and that's what we measure. So if you need a very high contrast to see things, you're not doing very well. If you see things in low contrast, you do very well. Okay? Now, the light level on the retina, as I said, the value of this background in terms of how much light per unit area of the retina you get is very, very important in determining how well you see. Now, the light level on the retina is in fact proportional to the luminance of the object you look at, which is how bright the object is, but also the area of the pupil, because the larger the pupil, the more light you capture. But because cones have directional sensitivity, you actually have to effectively apertize the area of the pupil, which means reduce it accordingly, because the more peripheral rays will not be absorbed. Okay, so the effective retinal luminance is given by this. Now, what Peter was talking about when he said that we took ages to sort of get going with the project is because we developed this technique where the pupil of the eye is measured in real time. So we know every 20 milliseconds what the pupil is. What we then do is we change the luminance of the screen, right, so as to make sure that the product of the luminance times the effective pupil area, which is given by that equation, is constant. So we can be absolutely sure that we have a constant retinal luminance, right, as seen by the cone photoreceptors. So these took a little while to do, but then we wanted to validate the technique. So what we've done was to choose an artificial pupil, which was again apertized for that size of 3.9 millimeters. The apertization function is as shown here, so that's the center of the pupil, and you see how it falls off. And then what we've done is to measure contrast thresholds for detection of this gap, okay, as a function of the luminance of the background. And we covered 4 log units here, so you know it's 10,000 range. And what was extremely pleasing was to see that this real-time technique, which uses a natural pupil, so you don't, it's not that pleasant to put artificial apertures in front and to keep them very close to the eye. So it's much better to be able to do these, okay, which means free pupil, free viewing, but you have a constant retinal luminance. But the two sets of results, the artificial pupil and the continuous closed loop feedback, okay, produce virtually the same results. So that is the first conclusion. The second conclusion is that as the light level drops, right, in the photopic range it doesn't make much difference. You can see 5% contrast under optimum conditions. And once you go into the mesopic range, which is here, you see all you need to do is to drop the background luminance by 0.5 log units, go from here to there, and you change the contrast you need to see that gap from 100% to 240%. So you see in this range, in the mesopic range, it matters enormously what the light level is on the retina. You very, very quickly lose the ability to see fine detail in low contrast. So this was a good sort of discovery. I'll come back to it in a moment. So we went on to investigate what would happen if you deliberately add a glare source, because obviously if you add a bright glare source, you are going to increase selectively the amount of veil, luminance veil you add to the image on the retina. So to do this in a quantitative way, what we've done is to produce this glare source. It consists of two quad LEDs with these spectral outputs as shown here. These were adjusted for D65, and then we had three glare conditions. No glare, the low glare condition, 1.35 lumens per meter squared in the plane of the pupil. Obviously, the more light you put in, the more glare you will get. And 19.2 lux, which is the high glare condition. Okay, now the test is very, very easy. Did you all see that? Did you all see that? And this time is high enough contrast to see the gap. Okay? So all the subject has to do is to press one of these four buttons to indicate where the gap is. So in this particular case, the gap is to the right, sorry, bottom left. So they press this button, bottom right, they press that button, top left, and so on. And then the staircases, right, for alternative forced choice procedure, adjust the contrast until you just don't see it. In fact, the threshold corresponds to 73% probability of detecting the gap. So what we've done is to vary the luminance of the background because we know that's important. So we used 1, 2.6, and 26 candelas per meter squared. We used these three glare sources. We used 40 subjects, admittedly virtually all of them recruited at UCL, right? We then measured each subject's ability to see these gaps, to see the fine detail, okay, for all of these combination of parameters. Now, as an example, look at these results here. I got to introduce you to these results. You see, the glare source is here. This location which was tested is 5 degrees away. That location is 10 degrees away. And this location is 15 degrees away. And those are plotted there. 5, 10, and 15. Can you see that? Now the glare source would be here. Now in the absence of any glare, these are the results. The green sort of symbols and line here. Those are the results. So the subject needs roughly 10 to 15% contrast to just see the gap. And that's typical of a normal eye at that like that. Then what happens is we turn on the low glare source, 1.35, and the results look like these. Sorry, look like this. They are in red. And it was really surprising that we are actually doing better with the extra glare, right? We would have expected to do worse because the retinal image contrast is reduced, right? So this was an important sort of observation to start with. If we now turn on the high glare level at 19.2, then what happens is at 10 degrees away, so 10 degrees away here and there isn't really much difference, but here, 5 degrees away, which would be about there from this bright glare source, the contrast goes up from 10 to about 28%. So that's a significant effect, there's no question about it, but that's consistent with large veiling glare and with this equation which tells us that the glare falls off rapidly away from the glare source. So by the time you get to 10 degrees and 15 degrees, there's less veil of light caused by the glare source. Okay, so this was an interesting observation. Then what we've done is to repeat the measurements in 40 subjects. And these are the data for all the subjects, so they're the average results. So remember what we are doing is we've got a glare source. We are testing at 5, 10, and 15 degrees away from the glare source. The glare source itself adds a veil of glare over the pattern. You see, whilst here, there's no added veil of glare. Now, the no glare condition is here, the low glare condition is there, and the high glare condition is here. And then each graph has a background of 1 candela per meter squared, which is effectively high mesopic, right, which is here. 2.6, which is there, and 26, which is here. So clearly one does best with the brighter background. So under optimum conditions, you need about 10%, this is the average for all these subjects, 10% contrast to see the gap, which then goes to 40% contrast at 1 candela per meter squared, right? Now, when you turn on the low glare source here, what is interesting straight away is that there's very little effect on the highest background luminance. There's virtually no effect. If anything, one does better. Okay, there is very small, if any, effect at 2.6 candelas per meter squared, and there's a very large effect at 1 candela per meter squared, as you can see here, except 15 degrees away, where again it's almost as it was in the absence of the glare source. But then what happens when we turn the bright glare source on, right, at 26 candelas per meter squared, which is the bright light level, we are not that handicapped, and this is an important thing that one has to realize. The reason why we don't suffer from glare is because most of our time is spent with the background being lit to a particular level, right, with some structure in the background and so on, and we're not really that affected. If you look at these results and those results, they're not that different. Then you drop the light level of the background to 2.6 and you really rocket up here to almost 80% contrast. And at 1 candela per meter squared, you go up to virtually 160% contrast. And this is really very high contrast to be able to see that gap. And the reason for it is because you are adding a lot of light from the glare source and you're reducing the retinal image contrast. And these results, remember, they're the average for 40 subjects. So they are representative of what really happens. Okay, now clearly adding the veil of glare reduces the contrast. This time the projector is on my side in the sense of one should be able to see it here, but there's nothing there. Now, what is of interest is to be able to really show the extent to which this scatter within the eye really causes the problems that we measure. Okay, so in order to do that, we really need to measure each subject's scatter function, light scatter function. Now, ideally what you should do is to have a very bright source to image what comes back from the eye and to be able to say that at a certain eccentricity away you have that much light, like that distance away. The trouble is you can't do that even with the most sensitive sensor because you need so much light with a point source that you would effectively burn the retina, and that wouldn't exactly be very useful. So what we actually do is to produce this extended ring, because every point on this ring is on a circle, is at the same distance away from the center. So all the points contribute scattered light here, but of course you've got thousands of points now on that ring. So the net result of it is that you get more scatter. and then we modulate the luminance of this ring as a burst of flicker, close to 10 Hertz. So you just get a burst of flicker, 340 milliseconds there, and when this modulates from 0 to maximum, it's usually only from 0 to 100 millimeters squared. So it's the kind of light levels that you have on a visual display. So it's not excessive in any way. And what happens is you get light that's scattered in the eye and ends up here over the dark trees. And it's modulated in phase with the scatter source. So you see flicker. You see that black disc flickering, right? Then what we do is we increase the luminance of the screen just over the dark disc and modulate it in counter phase. So when one is maximum due to scatter, the other one is 0, then it's maximum and 0, and so on. And as you can see, if you adjust the amount of light you need to modulate correctly, you cancel out the flicker altogether. But now that gives you a measure of how much light was scattered. Are you with me? Because it's the amount of light that you needed to cancel the flicker with. Okay, so and this is what the pupil does. It really constricts violently to flicker, although there's no change in mean light level. Okay, but fortunately by the time the pupil starts constricting, the stimulus is finished. Anyhow, these are the rings that we use, and when we measure the amount of light needed to cancel out the scattered light for various ring sizes, this is what it looks like. So now we use the equation which Peter described. This equation was introduced by Stiles, I think, and Crawford in 1938 or around that time. And Holiday before then, in fact. Yes, and it's an empirical equation, just happens to fit the data so well. So this is the equation fitted to the data. The beauty of it is that if you plot these results on a log-log scale, you get a straight line, and that straight line gives you a gradient and an intercept, and that gives you the value of k and n. Now, k tells you how much light is scattered in that eye, is proportional to the number of particles that scatter the light effectively. And the value of n tells you how fast the light drops off away from the glare source. Does it drop off rapidly, or does it drop off more gradually? Okay? So these are the data in the 40 subjects that took part in this study, and you see all the older subjects are over here in red, and the younger subjects are here in black. Okay? Now, case 1, there's no glare, therefore the contrast of the target is, as we define it on the screen, is the difference between the target and the background divided by the background, which becomes this, LT divided by LB minus 1. So that's the case of no glare. Case 2, with glare. Now, let me just explain these, because it's quite difficult. You know, we spend hours on these formulas, and now they're so simple here, right? But effectively, when you add a veil of light to the retina, you reduce the contrast, so you can't see the gap. So what happens is, on the screen itself, in the presence of glare, you have to put the contrast up more, so as to get to the same contrast that it would have had in the absence of glare. Then you see the gap. So that's the argument here. And the formula becomes this. The contrast with the glare source present is the contrast without the glare source, but it's multiplied by this LS divided by LB, which is the amount of veil divided by the luminance of the background. Okay, so what we do is we measure for each subject the scatter function of the eye. We now know how much light we are adding at 5 degrees, 10 degrees, right, and 15 degrees, and we can then calculate what the contrast on the screen should be if the only thing that affected the subject's threshold was the veil of light on the retina, was the decrease in retinal image contrast. Okay? So, these are the measured thresholds. So, what we have here for 2.6 centimeters squared is just one subject to give you the idea as to what we are doing. Okay? if you have no glare, these are the thresholds. With the low glare source, you do better. With the high glare source, you do worse for the nearest eccentricity. Now we use this equation. We know how much light we are adding at 5 degrees, 10 degrees, and 15 degrees for that subject. So we can predict what the thresholds should be. Okay? And to really cut the story short, you see that prediction there for the highest glare source. Those thresholds are much larger than what we measure. You see, it's about 55 here, and here is about 25. So it's virtually twice. So what is going wrong? Why is it that based purely on the veil of glare that you add to the retina, we are not actually predicting what we measure? We do much better, right? So that is the question. Just to show you that it applies to everybody, what we've got here is the low glare condition, and that's the high glare condition. And here we have 1 candela per meter squared for the background, so it's 10, 2.6, and 26, right? So that's what the graphs represent. And then for each graph, we have 5 degrees, 10 degrees, and 15 degrees eccentricity. Now, here, along the abscissa, we have the measured contrasts. Along the ordinate, we have the predicted contrasts. Now, I know it's a lot to take in here, right? But fundamentally, if there was a perfect correlation between what you measure and what you predict, all the points should be along that line. And obviously, within these measurement errors, they are along the line, here, there, and here, for the low glare level. But they are less along the line. In fact, there's a large departure for the low line level, okay, for the background of 1 candela per meter squared with a high glare source. So we are predicting a much worse performance than what we measure. And also for 2.6 candela per meter squared, by the time we get to 26, virtually there's no large deviation between what we predict and what we measure. Okay? So this is where the prediction fails, at low background levels with bright glare sources. So why? Well, we realized that when you add a veil of glare to the retina, you change the retinal sensitivity to contrast. So you can see better, right? Which is something that is not taken into account. So, you see, if you assume that you've only got the light scatter, which is causing the poorer performance, then this is the formula. If you now take into account the fact that when you add a veil of glare, you might be moving from this retinal illuminance to that retinal illuminance, so the contrast changes from 220 to 100. So the retina is doing better at detecting contrast changes. So if we take that into account, this is the predicted formula. Now again, it looks simple, but it has taken a few hours to sort of validate it. So now what we can do is we can apply the model, okay, but not just in terms of the light scatter, which produces that, but we can apply the model which takes into account the light scatter as well as the change in retinal sensitivity, and we get that. So now you see we actually sort of get a much better prediction for what we measure. So those are the predicted, this is measured. Okay, now I'll come to that in conclusions, right? But what it turns out, and let me summarize it in very, very simple terms, right? Don't bother to read that, just listen to me. Glare is obviously not a good thing. Disability glare, scattered light in the eye is not a good thing. But it's not quite as bad as it could be. And the reason for it is because as you add a veil of glare, you increase retinal illuminance. And when you are in the mesopic range, that improves sensitivity to contrast. Okay, so under some conditions, we actually see better with the glare source present. Now, the next topic that we tackled, which is connected with these, and there's no need to be too concerned because it's much shorter, okay, is to do with discomfort glare, when you have these bright lights in the visual field. And we started by literally just sitting down and thinking about it almost philosophically, right? What is discomfort glare and how does it come about? What effects do we notice and what effects bother us? So it was very logical to simply say that if you do get glare sources like these, you have a complete loss of spatial resolution over the source, which is accompanied by the perception of expanded edges and boundaries. And this is what you think of a bright glare source. That's what you think of it. And in fact, even when the light level is as poor as we get from this projector, right? So we're talking about 30 candelas per meter squared here. The appearance of that is unpleasant, right? So there are these psychological factors that contribute to what we think of as discomfort glare. And so is this one here or that one there. Now there's a glow within the glare source, right? So it's something that we don't really like to look at. If you happen to be glancing towards the glare source, as soon as you're aware of its presence, you almost pre-attentively look away. It's something that is to be avoided. The source is really too bright with respect to the surrounding background, and you see this here, you would say there's discomfort there, right? But it's only 30 candelas per meter squared, or less. But it's discomfort. Okay, so there are these aspects to glare that we really need to appreciate. Now, how does discomfort glare relate to disability glare? Well, it does relate to it because the more scattered light you have, forward scatter in the eye, the more you expand the size of the glare source, right? We can take what is known as the point spread function of the eye. This is the CIE point spread function of the eye, which tells you what the image of a point source is going to be like. But it also includes, the tail goes to about 10 degrees here, so it includes scattered light. We can convolve, I'm not so sure, are you familiar with convolution? You're not? Right. What we do is we effectively wipe these over the source like that. And at every point we plot the sum under that area. And this is what you get. So when you combine these with that, it's the same as passing these through the optics of the eye. That's what you get on the retina. Right? It's just that we can do it mathematically. So it's interesting because we do have these measurements of the scatter function of the eye. Okay. So the question of interest is, how does scattered light relate to discomfort glare? Well, it does, but it's in no way sort of discomfort glare, because you can get great levels of discomfort without any glare sources. Now, to really examine this experimentally, what we've done is to design a very uniform source of light by effectively integrating the light within an optical device. And then we place this in the center of this scene, which is an evening night scene from Crouch End, which I happened to have at the time, so great, let's have it there and make it into a large print. Place the sources behind. Under computer control, we can change the area of the target very easily. We measure the pupil size, and we can present these glare sources at various intensities to the eye. The glare source is again generated from a quad light emitting diode controlled accurately so that we can have a range of light levels, 3 log units coming out of it. So this homogenized glare source allowed us to measure the level at which the subject experienced discomfort glare. And we could do this for any source size we wanted. Well, within a limited range, in fact. Now, what we measured the total amount of light that enters the eye when the glare source comes on. We measured the pupil size, glare source size we knew because we fixed it, surround luminance we knew, pupil plane illuminance, and source intensity. And the measurement variable in this test was the retinal illuminance. So it was really the product of the luminance of the source and the area of the pupil. And we employed a staircase procedure. All the subject had to do was to press one button to say, yes, I have seen or experienced discomfort glare, or no, I haven't. So the program then produced a level of retinal illuminance that represented the threshold for discomfort glare. Now the results were really quite surprising, well, at least to us, because we're obviously not exactly in lighting. But what was extremely interesting is this is the threshold in log trolens. So the threshold represents the amount of light per unit area of the retina that you needed to just see discomfort glare. And this was defined very clearly, is when you lost spatial structure within the target, when the edges started to expand, when it glowed, all the kind of features that one would normally associate with a very bright street light. Okay, so what was interesting was that as you change the area of the target through a considerable sort of range here, we get very little change in discomfort glare thresholds. They're slightly higher for smaller target sizes, but the effect is not really that significant. On the other hand, if you plot the illuminance level in the plane of the pupil caused by the glare source, right, you see you start here with a low level and then it goes there, and that's plotted here, to a very high level. So what does this really mean? It really means that if you happen to be on the street, you have a light over there, you look at it, right, and if it produces the right kind of horizontal illuminance that you want to have, it will glare like anything if it's small, but if it's large, right, you would produce the level of horizontal illuminance that you want, which is I, without actually producing an unnecessarily large level of discomfort glare. So this has got immediate practical applications. It's probably not something that it's so novel, but it's nice to see quantified in terms of glare thresholds. So the average data for the 50 subjects showing very much the same kind of effect, slightly greater dependence on glare source size. So for the smaller glare source size, you have slightly higher thresholds than you have for the largest glare source size. And there are reasons for that. Okay, what was extremely interesting is that there isn't a strong dependence on age. Right, I'll come back to this in a moment. So, target size has a small effect. There's little dependence on age. But what the results show is that you can achieve a high level of pupil plane illuminance, which in real life would be equivalent to, for instance, pavement illuminance, right, without actually causing significant levels of discomfort glare by just using a sufficiently large source size. Now, what are the key mechanisms that mediate discomfort glare? Well, we switched back to our philosophical mode and decided that we really got to analyze what is actually happening. We get this complete loss of spatial resolution, spatial vision, all the edges and fine detail disappears, boundaries expand, there's a glow within the glare source itself. You try to avoid it, and really the conclusion, the source is far too bright for that background. So what does that point towards? Well, it points towards saturation of some mechanism within the eye or the visual system, possibly saturation of photoreceptors in the retina. And when you get this saturation, you get saturation which is then propagated along ganglion cells, along detectors which respond to light flux, to contrast, and this saturation produces the effects that we've got here that we label as discomfort glare. Okay, so the message to really take home is that you should not have retinal luminances much higher than 5 octorods. If you do, you are likely to cause discomfort glare, irrespective of the size of the target. Discomfort glare really combines the effects of a number of perceptual characteristics, but they all seem to link to saturation of responses. Okay, interestingly, the pupil continues to respond, to constrict more, even when you exceed the discomfort glare threshold. It is simply because there's so much light that is scattered outside the glare source, which hits unadapted areas of the retina, which then drive the pupil. So I think those are really the fundamental findings, and I'm going to leave it to Peter to summarize what the implications of these findings really is. We acknowledge EPSRC, as Peter mentioned, this kind of project, which is extensive in terms of examining so many aspects of disability and discomfort glare, we would not have been able to carry it out without support from research councils. And these are the people that contributed to these two aspects that we discussed. And now back to Peter.
Okay. So, John did a big study in lab cases, but the bit that worried me was, does this actually mean anything for road lighting? So, what we did at UCL was we said, well, how can we make this work in a simulated road lighting situation? And so what we did was we had John's basic principle of a target adjusted so that we could find the contrast threshold, that which it just became visible, and we played with the background luminance, the glare source position, the glare source colour, the glare source size, and the luminance at the eye, the illuminance at the eye due to the glare source. And essentially, that looks like almost a repeat of the previous slide, so we'll skip. So we had a scene like this, which we took to be a reasonably standard nighttime scene. And there is the potential in this scene for a black dog to appear and about to run across the road in front of you. And we could change the contrast of the dog, and it could face into or away from the road. And so what you would see is a contrast ring. Now, I think black dog's about there, but we've been lost to veiling luminance from other sources. And essentially what would happen in practice is that that would flash on for about 650 milliseconds, which would just give you time to find the dog, scan your eye to it, and be able to report its orientation if you saw it. So the net results of this were pretty much similar to what John found. The effective contrast at the eye, at the retina, went down. So you were actually, the boost you were getting in the retinal performance due to the veil of light scattered on the eye agreed with what John's findings. However, that because we were doing ours in a more real situation, there was significantly more scatter in the results. So essentially, it proves that the theories that we've tested for disability glare works in the real world, or something more akin to the real world. I think it would be a dangerous experiment which we wouldn't get past the ethics committee, to actually have someone in the middle of the road watching the traffic go by and waiting for this occasional stray dog to turn up. So, what does the findings of what we've done mean for A, discomfort glare, where we have, as current practice, based on the G-class system, and what does it mean for drive when we're working glare for drivers based on the threshold increment control system? What problem with the gear class system is it controls intensity. And we all know that the intensity of a source is related to the luminance by dividing it by the area. So at the moment we're controlling intensity, and as John showed, intensity would be proportional to a luminance at the eye for a fixed condition. So clearly a larger light source will be less glary than a smaller light source. So what are we doing in our light source design at the moment? This is a typical luminaire, probably made 10 years ago, where we have an IEDE lamp where the luminaire, this optics flash a relatively large area and is able to control light. And now we've moved to something like this, where we've got a series of tiny little light sources. So in practice, the area of our light sources has dropped by an order of magnitude, and so the luminance has gone up by an order of magnitude, so it's no wonder that anecdotally we're getting more reports of glare in street lightings with modern lanterns. And basically, the G classes that we currently have are not suitable means to control that in any way. So the measure of disability glare, as I said earlier, is this veiling luminance function, which is a direct function based on the veiling luminance, a direct function based on threshold luminance is based on veiling luminance. Now, the first thing we found from this experiment was that nobody has, I'm pretty sure nobody has a value of K equal to 10 and a value of N equal to -2. Everyone is different, and there's a wide scatter, and in general it changes with age, and so the veiling luminance formula needs to be reviewed, particularly as the demographic of the drivers on the roads at night is changing. And secondly, this formula does in no way accounts for the fact that we get a significant boost, particularly in the high mesopic at around about 1 candela per square metre, which would be not unreasonable for say a traffic route in London ran by TfL. They would like probably to 1 candela per square metre, and therefore this formula would be totally wrong for that. At that point, I think I'd like to come to the conclusion. So the current formula for the calculation of valent luminance doesn't take into account subject differences, and the formula for TI is just plain wrong. Discomfort glare G classes control totally the wrong parameter. Luminance is the critical value, not intensity. Incidentally, as a side step from this project, we actually went on to take the concept of, does this saturation of the retina have an impact in the brain? And it seems to. Our fMRI studies have shown hyperexcitation in particular areas of the brain. It's a whole new subject that we could start to talk about, and we could spend another evening talking about that at some time. But so it's interesting to note that the mechanics of what we've found and the practicalities still work, and that this situation is that at present we have totally the wrong parameters in our street lighting control metrics. They're totally controlling the wrong thing. So lighting practitioners in the room know you've got to go out and do something about it. And at that, I'd like to say thank you all for attending, and in particular, thank you, John, for a really excellent core of this lecture. Thank you.
Okay.
Okay,
So
question.
lighting practitioners need to go out and do something to the streets. What could you do there when the cars are being currently done with the running boards that are EU directives? So
They're not EU directive.
is it not?
No,
That's what I was
no.
told.
The EU
Okay, so
directive,
well,
the
well,
EU
whether it's
directive
not, but
mandates
we've got-
the
If I can
intensity.
just finish, then we nonetheless have cars on the road, have the upside down eyebrows on
Yes.
the
Yes.
headlights, and they've got braking lights that can light up all over the back of the car and maybe in multiple strains. None of that is actually, as I understand it, controlled. So lighting practitioners, what do you do about when car manufacturers, because I don't know the science behind how the cars are now being
Peter, I might be able to just add a bit to that. I've been doing some work looking into illumination of road traffic signs, and one part of that is to actually understand how car headlights work. And it's the United Nations who control the standards. There's 5 regions globally that those standards are for. And as much as I understand so far, talking to the manufacturers and the people responsible for the standards, is, as you say, daylight running lamps is actually proven to reduce accidents and pedestrian collisions. But the problem is that as you get in towards the night time, that they become too much of the discomfort and actually work the way. So I think now they're actually looking at actually dimming them, or even in some places they will extinguish when the vehicle headlights come on. So I think the standards in that area are moving on. And likewise, as a driver, following vehicles behind where you've got these LED lights coming, I tend to find certain on old ones they flicker, and I find that to be a discomfort as well.
Yeah.
So
There's an issue with flicker, but also most of the standards for vehicle lighting are all intensity standards. There are very few luminance standards, and unfortunately there are 2 major research centres in the world into vehicle lighting, and unfortunately they all have to be paid for, and they really, I think, have turned into people who make excuses for more glare. Yeah, and there are only two major centres that I'm aware of that do this research. One in the United States and one in Germany. So I think we need to start talking to some of the people.
yeah.
I think it's our friends in University of Michigan are probably beyond redemption, but maybe we can have a go at the University of Paderborn.
Or you could just do more research on road users.
Pardon?
You could do more research on road users and actually have more of a public awareness, and point out to the industry or to whether it's the United Nations or the EU who are making cars have these LED things
I mean,
all over them.
the problem at an EU level is that the regulators aren't particularly worried.
No.
It's delegated down to the industry.
I think
So this is what I'm saying.
Yes.
More noise needs
More
to be
noise
made
needs
about it.
to be made.
I don't want to be particularly sort of like, hello me, I'm important, but I did do one small study on taxi
Yes.
drivers in
Yeah.
London, where we just shoved a questionnaire through the windows of taxi drivers.
Yeah.
We got about 180 or something like that questionnaires back, and we just asked them, as London taxi drivers, about glare and their perception of glare from headlights, from indicator lights, and from braking lights, and they did say that they found that there was a significant increase in their symptoms of discomfort glare.
Yes.
We were particularly interested also then in headache, because that's my interest, as in visually triggered. So more than just discomfort, the signal that can go on from that. And the younger drivers also said that they did have headaches triggered. What did they do? Did they pull over? I didn't ask that in the questionnaire, and I didn't wonder about it. But it was the braking lights. It was
Yes.
that flashing on, off in London, or as a taxi driver because you're in traffic. So there's discomfort there. There's also, sorry, I'm trying to raise things that haven't been covered in the talk. There is discomfort glare. You could just look at it and look away, or if you're in an industry that is, or your occupation is something where you've got it in your face day in, day out, I don't think that's under researched.
Yes, no, I fully agree that there is a big issue there of vehicle lighting. There are also other things going on. Because one of the things that is happening through changes in the way street lighting is provided is that our roads, the borders of our roads are getting darker. and so the impact of glare is now worse. So you might think, it's sometimes been argued, and I've seen some people who work in dynamic glare have argued that the actual role of street lighting is to try to reduce the impact of vehicle glare. And there's a good argument that in the UK highway network that is very much the case. There's an interesting experiment that the Highways Agency are doing at the moment, one we couldn't get ethical clearance for, but they're able to do it fortunately. And what I've often said is it would be good to be able to take sections of highway, shut off the street lighting and see how many people you kill. And the Highways Agency can do this experiment, we can't.
Yeah. Again, I think one of the interesting things is I'm a street lighting practitioner. One of the things that my interest in glare comes from the fact that I've noticed there's an increasing amount of cyclists, certainly in where I live, well, probably nationally, these high intensity LED lights that are coming to a point. I'm talking to British standards, that there's British standards that are so old, or European standards are so old, that these are imported from America. They're not regulated, not controlled, and are actually becoming a real nuisance on the road. Also, the other thing I find is a big problem are emergency service vehicles at night with their blue LED lights flashing. I actually find they're more of a problem and should actually be dimmed. And again, something else I have an interest in, I own those kind of lights as well at work, and you can dim them. And the British standard, last time it came out, because of the current problems with austerity and energy costs, we dropped everything by a lighting class. And the one thing that constantly keeps bugging me is, as an industry, we're all making these decisions without talking to each other and understanding what's going on. And I think the work that you've done here, whilst probably a lot of it goes over my head, but I get the gist of what you're saying. But the reality is that we need to talk. We are human beings. We interact with the environment around us. And you've got people doing car lighting, you've got people doing road lighting, all these various things, but we don't actually understand how it all impacts on each other. And that's fundamentally wrong.
Yeah, I agree. And also on the cycling thing, I mean, when you've got very high intensity cycling, I've had some correspondence, and it makes the cyclists think, oh, I'm lighting myself up like a Christmas tree, but actually it makes a driver who's following find it difficult to judge the depth of where the cyclist is in front of them, so they actually make themselves a bit more vulnerable instead of being lit up like a Christmas tree.
Yeah.
So, but I don't, so how do we know?
I mean, the only thing I would say is that we do have the ability to sense the environment and control lighting much, much better than we ever had before. It's just that we don't do it. And now we also know roughly how various changes like background lighting, like the retinal luminance produced by glare sources and so on, how they affect discomfort and the perception of glare. And as an example, for instance, you can increase the lighting within the car, and that undoubtedly reduces the effects of discomfort glare, right? You can't increase it too much, because if you increase it too much, then you will fail to see things outside, okay, which happen to have low contrast. But there is a trade-off. Unfortunately, that trade-off requires a little bit more research and automation, so that, I mean, an expensive car now provides so many of the features that would easily be incorporated in terms of lighting. You see, a certain amount of ambient illumination within the car is actually a good thing as far as I'm concerned, because it does reduce the perception of discomfort glare. You don't want it, but that has to change. You've got to sense what's outside, adjust things inside. I mean, a cockpit is a beautiful example, you know, of a good design. You go into the cockpit and then you spend a couple of hours there and you go into the dark, and quite honestly, you still retain the perception of color, you still retain good acuity, but everything changes. All the displays change automatically.
Might I make a suggestion that we stop our discussion now, we move upstairs and continue the discussion in the presence of some wine?